Bismillahirrahmanirrahim. Now we're going to continue our statics revision, equilibrium of a body on a rough horizontal plane. We have this example: a body of weight W is placed on a rough horizontal plane where the measure of angle of friction between the body and the plane is lambda. The body is pulled by a force inclined to the horizontal with an angle of measure theta upwards. Find the least force P make the body is about to move. Here we have to sketch this problem. We have this rough horizontal plane and we have this body placed on this plane, okay, and we have here an external acting force B inclined to the horizontal with an angle of measure theta upwards like this. It's required to find B minimum as the body is about to move, okay. Here we have an equilibrium situation as the body is about to move, and the direction of expected motion in the acting force in B in this direction, okay. As we have to apply the steps of solution of this kind of problems, first we have to identify x and y. X is horizontal, okay, and perpendicular direction is y. Okay, number two, we have to identify the forces acting upon this body. We have here, of course, the weight of this body acting vertically downwards in this direction, and this is W. Okay, we have here normal reaction of this rough horizontal surface on this body. We have here N. We have this external acting force P. Okay, then we have also the friction force as the surface is rough. Then we have here the expected motion direction in this direction. In opposite direction, in this direction, we have a friction force, and in this case, a friction force is limiting friction force as the body is about to move. Then the body, okay, is about to move. Then we have F equals Fs equals mu s times n, as mu s is the static friction coefficient between this body and the surface, and in this case also mu s equals 10 lambda, where lambda is the friction angle between this body and this surface, okay. Then last step, we have to apply the equilibrium equations. We have two equations: summation of x equals 0 and summation of y equals 0. The component of the forces in x direction, as we assumed in horizontal direction, equals 0, and in y direction equals 0. We'll start with summation of x equals 0, okay, but first we have to resolve this inclined force in two orthogonal direction, in direction of x and y. Then we have here b cosine theta, and in this direction we have b sine theta, okay. Now we can apply this equilibrium equation: summation of x equals 0. We have here b cosine theta, okay, the forces indeed in this direction equals the forces in this opposite direction, equals Fs, and Fs equals mu s n, okay. This is equation number 1. We have summation of y equals 0. Here we have n plus b sine theta equals w. Then we can find n from here. Then n equals w minus b sine theta, and we can substitute in this equation, okay. Then we have b cosine theta equals mu s is 10 lambda. Then we have sine lambda over cosine lambda multiplied by n, which is w minus b sine theta, okay. Then here we have to multiply both sides by cosine lambda. Then cosine theta cosine lambda equals w sine lambda minus b sine theta sine lambda, okay. Now we can move this in this side. Then we have b as common, cosine theta cosine lambda plus sine theta sine lambda, okay. This is equals w sine lambda, okay. As we know, this quantity inside this bracket, cosine theta cosine lambda plus sine lambda, cosine sine plus sine, this equals cosine difference, the difference between theta and lambda, okay, or lambda minus theta equals W sine lambda, okay. Then we can find B equals W sine lambda divided by cosine lambda minus theta. It's required to find B minimum. B minimum, then this denominator is maximum, okay. Then we have here cosine lambda minus theta is maximum, and as we have a maximum value of cosine is 1, okay, where is 1, then B minimum equals W sine lambda, and this is required to find. This condition we can find when lambda minus theta equals 0, then lambda equals 0 equals theta. This is a situation where we find B minimum, okay, that makes the body is about to move. Then B minimum equals W sine lambda, and this is required to find. We have another example. In this figure, we have a body placed on a rough horizontal plane, okay. The weight of the body is W. Lambda is the friction angle. The body is tensioned or pulled by this acting external force B in this direction, inclined upwards to the horizontal with an angle of measure 2 lambda. It's required to find B as the body is about to move in terms of W and lambda, okay. Here we have to apply the steps of solution. Here we have B, and this angle is 2 lambda, okay. First one, we have to select X and Y direction. Horizontal, we'll assume horizontal direction as X and vertical direction as Y. Number 2, we have to identify forces acting upon this body. We have weight W acting vertically downwards like this. We have normal reaction here, okay. We have, of course, this external force P, okay. And as the body is about to move, we need to identify directions, expected motion direction, okay. As B acts in this direction, then the expected motion direction in the direction of the acting force P in this direction. Then in opposite direction, we have here friction force F, and in this case it's limiting friction force as the body is about to move, okay. Then we have friction force equals Fs equals mu s double times n, okay. And in this step we have to resolve this force in two orthogonal direction. In this direction B cosine 2 lambda, and in this direction B sine 2 lambda, okay. Finally we have to apply equations of equilibrium of this body as it's about to move. Then it's in equilibrium state. Then we have summation of x equals 0, summation of component of force, the component of the forces in y direction equals 0 as well, okay. We'll start with summation of x equals 0. Here we have b cosine 2 lambda equals fs equals mu s times n, okay. And as the body is about to move, also we have mu s equals tan lambda, as lambda is the friction angle, okay. Then we have here mu s equals tan lambda, okay. This is equation number 1. Second equation, summation of y equals 0. Then we have b sine 2 lambda plus n equals w. Then we can find n equals w minus b sine 2 lambda, and we'll substitute in this equation, okay. Then we have b cosine 2 lambda equals mu s equals tan lambda. Then we have sine lambda over cosine lambda times n is w minus b sine 2 lambda, okay. We'll multiply both sides by cosine lambda. Then we have b cosine 2 lambda cosine lambda equals w sine lambda minus b sine 2 lambda sine lambda, okay. We'll move this in this side. Then we have b as a common, cosine 2 lambda cosine lambda plus sine 2 lambda sine lambda equals w sine lambda, okay. We have cosine sine. This is b equals times cosine, Okay, the difference between 2 lambda and lambda, then we have cosine 2 lambda minus lambda equals W sine lambda. Here we have B cosine lambda equals W sine lambda. Then finally the force P equals W tan lambda, and this is required to find. An example here in figure, the weight of the body is W. Okay, and the horizontal plane is rough. R dash equals 90 Newton. Theta equals lambda equals 30. The body is in equilibrium. Find B and W. Here we have this rough horizontal plane. Okay, and this body placed on it. Okay, the body is acted by this external force P inclined to horizontal with theta. Okay, and we have here resultant reaction force R dash equals 90 Newton. Okay, then we'll assume x and y in horizontal and vertical direction, x and y. Okay, number two, identifying the forces acting upon this body. We have this external force P, and we have this resultant reaction, and of course we have here W, the weight of this body, and it acts vertically downwards like this. Okay, then the body is in equilibrium as given in this problem under the action of these three forces P. Okay, we have B and R dash resultant reaction force, and we have of course W, the weight of this body. Okay, also we have theta equals lambda. Theta equals the friction angle lambda. As this body is in equilibrium under the action of these three forces, then we can apply Lamb's rule as follows. Okay, then we have R dash divided by the angle inclined confined between B and W. We have here this 90 and theta. Then we have sine. Okay, and theta here equals 30 degrees. Then we have sine 120. This is equals B divided by sine the angle confined between R dash and W. Here we have this right angle. Okay, as we know, if we resolve this R dash into two orthogonal components, then we have here N and we have here friction force. Okay, the angle between N and R dash is lambda, angle of friction, and this is equal 30 degrees. Okay, then we have the angle between R dash and W. This is equals 150. Then we have B over sine 150. This is equals W divided by sine the angle between B and R dash. Here we have this 30, and we have this 60. Then we have here right angle between B and R dash. Here we have sine 90. Okay, it's given that R dash equals 90 Newton. Okay, sine 120 root 3 over 2. This is equals B over sine 150 1 over 2. Okay, equals W over 1. Okay, from here we can find W equals 60 root 3 Newton. Okay, and B equals 30 root 3 Newton. Okay, this is the simplest way to solve this kind of problem. We can also apply the normal steps for solving this kind of problem by resolving B, okay, in two orthogonal direction, and R dash in N and mu S, and complete our solution, and we'll find finally W equals 60 root 3 and B equals 30 root 3 Newton, and this is required to find. We have another example. A body of weight 64 Newton is placed on a rough horizontal plane and acted upon by a force of magnitude 40 Newton inclined at theta 2 horizontal, such that the magnitude of the resultant reaction force is 40 Newton. Okay, find in the case of equilibrium sine theta and mu s. Okay, first we have to sketch this problem. We have this rough horizontal plane, and we have his body of weight 64 Newton placed on this horizontal plane and acted out by a force, external force, for example P here equals 40 Newton. Okay, inclined at theta to the horizontal, such that the resultant reaction force R dash equals 40 Newton. Okay, It's required to find sine theta and mu s static friction coefficient between this body and the horizontal plane. Okay, we'll assume first x and y in this direction x and this direction y. Okay, we have to find or identify the forces acting upon this body. You have this external force. We have here W. Okay, W equals 64 Newton acting vertically downwards. We have here N, normal reaction force. Okay, as it's assumed that the body is about to move in this direction. Okay, then we have in opposite direction this limiting friction force Fs equals mu s times N. Okay, and finally we have to resolve this into two orthogonal direction. We have here in this direction B cosine theta and this direction B sine theta. And now the time to apply equilibrium equation. We have summation of x equals 0, summation of y equals 0. Okay, here we have B cosine theta equals mu s times n, and this is equation number 1. In y direction we have n plus b sine theta, n plus b sine theta equals w. Okay, then we have n equals w minus b sine theta, and this is equation number 2. Okay, it's given that r dash equals 40. Then we have r dash equals root n square plus n squared mu s square. Okay, here we have we can substitute here from equation number 1 and equation number 2 in this r dash. Then we have here root, okay, n squared is w minus b sine theta all squared plus okay, we have n squared mu s squared. From this equation we can squaring the two sides. Then we have here n squared mu s squared equals b square cosine square theta. Okay, now we can squaring both sides. Then we have r dash square equals w minus b sine theta all square plus b square cosine square theta. Okay, here we have this 40 square equals, we have w 64 minus 40 sine theta all square plus 40 square cosine square theta. Then we have this equals 64 square minus 15120 sine theta plus here we have 40 square sine square theta plus cosine plus 40 square cosine square theta. Okay, then we have here 1600. Here we have 4096 minus 1 here we have 5120 sine theta. Okay, here we have plus 40 square as a common sine square theta plus cosine square theta. Okay, then we have this term equals 1. Then we have finally 1600 equals 4096 minus 5120 sine theta. Okay, plus 1600. Okay, we can remove this with this. Then we have here 5120 sine theta equals 4096. Then sine theta equals 4/5, and this is required number in number 1. Okay, to find mu s we can substitute in this equation. We have from equation number 1 b cosine theta equals mu s times n, and we have here n equals w minus b sine theta, w minus b sine theta. Okay, now we can substitute. We have here b equals 40 cosine theta, we can find cosine theta as we have sine theta. If we sketch this right angle triangle, okay, this is theta, and we have sine theta equals 4 over 5. Then we have cosine theta is 3 over 5. Then we have here 4, 0. Cosine theta is 3 over 5, okay, equals mu s. It's required to find mu s. Okay, times w equals 64 minus b here. B is 4, b is 4, 0 times sine theta is 4 over 5. Okay, then we can find mu s equals 3 over 4, and this is required second.